Duality linear programming problem, LPP, linear programming problem. So first of all, we have to understand what is the meaning of duality. So every LPP is associated with a kind of problem which is called the dual problem. And LPP can be written in the form maximize a function f x is the solution of that function C transpose x. Okay, C is a matrix and you have written in the transpose form because the answer will come in the form of transpose. Subject to Ax is less than equal to b and x is greater than equal to 0. Okay, this is a kind of linear programming problem. Okay, you already have studied this kind of problem and I hope you have the idea what is the LPP. The dual problem, what is the dual of this problem? Dual of the same problem. In this case, what we do, in the place of maximize, we write minimize. Okay, everything will be reversed. Minimize. Okay, what thing we are going to minimize? We take another function g of y. Okay, and g of y equal to bty. Okay, what is b? B is here. Okay, the same b which is given in the given condition will come in the solution of the dual, and likewise the condition of the dual will be the solution of the actual problem. Actual problem is termed as the primal problem. It is known as primal. Okay, so the actual problem is the primal problem and this is the dual problem. So we take this part as the main part and this part as the condition part. This part as the condition part here. Subject to A transpose of y. That means this part. A transpose of y. Here this is greater than equal to, this is less than equal to. So it will now become as greater than equal to, and you will take C because I have told that this will come here and this will come here. Okay, this is the solution of the primal problem and it will come into the condition, and the condition of the primal problem will come to the solution of the dual problem. Okay, I will also give an example so that you will be easily understand this thing. And because you have included a variable y, therefore the variable y should be greater than equal to 0. Okay, it should not be negative. So this is the actual problem. It is called as primal problem, and this is the dual problem of the same problem. Likewise, this is the dual and actual problem. So what are the basic properties of the dual? First of all, we have to understand this thing. We have to understand this thing. I have written at the same place here. कोई बात नहीं. Properties. What are the property? Number one, every linear programming problem is associated with another closely related linear programming problem, and its name is dual, as I am explaining here. Number 2, the two relations are such that the optimal solution of one problem can be used to obtain the optimal solution of the other, just like I have explained above. And number 3rd point is, it is important as sometimes solving dual problem is more convenient than solving the actual primal problem. Okay. Suppose I am saying that you are going to attend the Integral University offline classes. Okay. Then there should be some conditions. Okay, there should be some conditions for that. The first condition, condition 1, you should be non-COVID. Okay. Number 2, you should be submitted your fees. Number 3, a course would have allotted to you. Okay. Number 4, a teacher would have allotted to you. Okay. So likewise there can be so many conditions. So you can say that the first condition is A1, it is B1, it is C1, it is D1. So in this way you can write the equation as A1 x1 plus A2 x2 plus A3 x3 plus A4 x4. Okay. These conditions should be followed. Okay. These conditions should be satisfied. So it should be equal to or greater than 0. Here I have written A1, A2, therefore it should be A1, A2, A3 and A4. These are the conditions. So in this way the linear problem can be defined. In this way the actual linear problem can be defined. So in this there should be the dual problem. In that case the dual problem may be more easy than the actual problem. Now here I am going to discuss some of the basic property of the duality problem in the form of theorem. What will be the theorem? Theorem number 1. Its name is weak duality. Its name is weak duality theorem. The theorem is saying that if x and y are the feasible solution, the theorem is saying that if x and y are the feasible solutions, if x and y are the feasible solutions to the primal as well as dual problem respectively, then fx must be less than or equal to gy. Okay, where x is the actual or primal and y is the dual. So how would you prove it? The proof is very easy. The condition of the primal is given here. What was the condition of primal? Fx equal to Ctx. So I am going to write here as Fx equal to Ctx because it is the basic definition of the primal. Fx equal to C transpose x. Now, what is C? From here, C equal to C equal to AY. Okay, actually ATY is greater than C. ATY is greater than C. So I am going to write this thing here. The condition is that A transpose Y is greater than equal to C. So in place of C, we are going to place this thing. Okay, we are going to place this thing. So how we can write is if we write in the form of transpose, then this sign will be changed. So it will be greater than equal to. Okay, it will be greater than equal to, and in place of ATY, it will become YTA. Okay, it will become YTA. This is the matrix property. So in place of CT, we can write as YTA. Okay, and because we are writing one thing is that this is only change, therefore this will remain as same, it will not change. Okay, it will not change. It will be changed in the form of dual, and we are not calculating the dual, we are just changing the dimension of M and N. Okay, M are the row and N is the column, and we are just exchanging the dimension, and therefore this sign will not change. So in place of CT, we are going to write YT A, and X will be there, and because this is larger than CT, therefore the lower side will be larger than or equal to the above part. Okay, and in place of YTA, A is the matrix, therefore I should have written in capital. Okay, because A is the matrix, and the smaller is written in the form of constant in mathematics. Okay, so because A is the matrix, therefore we should write it. And what is AX? We know that AX equal to B in the form of matrix. Okay, so in place of AX, we are going to write as B. Here also AX equal to B. Yes, AX is less than equal to B. Okay, AX is less than equal to B. So AX is less than equal to B. So in place of AX, we can replace it by B, and YT will remain and same, and because lower side is again greater than equal to the upper side, therefore this sign will remain here. And what it become YTB. See here, in the form of dual, YTB. Okay, YTB is just the change of this one. Okay, YTB is just the change of this one, therefore it will be written as YTB. It will be equal to G of Y. So in this way we have proved that Fx is less than equal to Gy. Okay, because we have started from the actual function Fx and we reached to the right side function Gy, and because the two signs are less than equal to, therefore the theorem has been proved, and this implies that Fx is less than equal to g of y, hence proved. Okay. Now I am going to prove one more theorem here. One more theorem. It is the duality theorem. Theorem 2, duality theorem. Duality theorem. What this theorem states? Let us write it first. If either of the primal and dual problem has an optimal solution, यानी कि प्राइमल ड्यूअल में से कोई एक अगर ऑप्टिमल सॉल्यूशन रखता है, सो डस द अदर एंड देयर ऑप्टिमल वैल्यूज आर इक्वल. ठीक है, तो दूसरे की ऑप्टिमल वैल्यू जो है वो आपका जो है फर्स्ट वाले ऑप्टिमल वैल्यू के बराबर ही होगी. आई एम राइटिंग द स्टेटमेंट. इफ either of the primal and dual problems has an optimal solution, so does the other and their optimal values are equal. This is the statement of this theorem. ठीक है. If either of the primal and dual problem has an optimal solution, so does the other. यानी अगर एक जो है optimal solution रखेगा तो दूसरा को भी optimal solution रखना पड़ेगा, है ना. If one has the optimal, then the other should also have the optimal solution of the same problem, and that values must be equal. This is the statement of theorem, and we are going to prove it. Proof. So first of all, we have to proceed by taking an optimal solution, because the statement is saying that there must be an optimal solution. So let us take, first of all, let x0 is the optimal solution. x0 is the optimal solution. So if f0 is the optimal solution, therefore f of h0 it should be satisfy the primal equation. Okay, because this is the solution of that equation. Therefore, if you put this value into the primal equation, it should satisfy. So we can write it as CTX, because I have already written that fx equal to CTX is the primal equation, subject to, because in the linear equation there are two things. One is the objective function, this is the objective function, and this is the condition, subject to a x0 is less than equal to b and x0 must be positive number. Okay, so till now we have considered x0 is the optimal solution, and because it is optimal solution, we can write the primal equation as this one. Now consider the inequality. Consider the inequality of dual. Okay, the dual of this problem will be a ty should be greater than equal to 0. Okay, this is the duality of the above equation. So we can write B transpose y should be less than C transpose x0, for y greater than equal to 0. Okay, because this is the dual, I have already explained this. So its value must be less than equal to this value, because I am saying that it is the optimal solution, and because x0 is the optimal solution, so its value must be larger than the dual of the same problem, because dual and its primal will be having the same kind of solution. And in the theorem we are saying that one of the primal and dual will be having the optimal solution. So optimal means the maximum. So if x0 is optimal, then its value must be larger than all the other value, including the dual of the problem also. bty is the dual, and therefore its value must be less than the optimal of the primal also. Therefore I can write this thing clear. I think it is clear now. But from the weak duality, at the above I have proved one of the theorem that from the weak duality theorem, we know that I just prove it, f x0 is less than equal to gy. Okay, if I start from a primal problem, then it will be moved into its dual problem like this. I just prove it in the weak duality theorem. So by this thing, f x0 must be less than equal to gy, and because it is less than equal to gy, and here it is larger than the its dual, therefore the dual and the primal both are larger than or equal to each other, and therefore we can say that both are actually equal, and therefore the optimal solution of the primal will be same as the optimal solution of the dual, otherwise it will not be same. Okay, clear? Here I am saying, here this theorem says that the primal is larger than the dual, and by the weak duality theorem the dual is larger than the problem or equal to. So both are larger than to each other, therefore in actuality they are equal. Okay, therefore if this is optimal solution, then y must be optimal also. So this is the statement of the duality theorem. Okay, hence it is proved again. That is, so if this is larger than this, we can write it as its condition ct x0 is less than equal to bty. This is equation number 1 and this is equation number 2. So merging equation 1 and 2, we get actually ct x0 is equal to bty, but we have supposed that x0 was the optimal solution, and therefore y should be the optimal solution also. So okay, this implies that y is optimal too. Okay, so in this way this theorem proved again. Okay, last theorem of this chapter, unboundedness theorem. Theorem is unboundedness theorem. Unboundedness. There are two kind of set. One is bounded set and other is unbounded set. Okay. Suppose I am writing a set, a very simple set, 1, 2 and 3. Okay. So if I am writing this kind of sign, then it is bounded. It is bounded. Okay. And if I am writing this kind of thing, then it is one thing, it is bounded. Okay, either we write this kind or this kind of sign, both are bounded. Okay, the only difference between these two is that in the actual set 1 and 3 are also included in this case, but in this case 1 and 3 are the outside of the set, okay, but all the other values are inside the set, okay. That means 1 plus epsilon is inside the set, 3 minus epsilon is also inside the set, where epsilon is tending to 0, okay, but actual 1 and 3 are not in the set, okay. So this is open and this is closed. What is unbounded? Unbounded means if I write 1 2 3 up to infinity, okay, so we don't know what is the upper limit of this one, therefore it is unbounded, okay. In the form of curve, I am giving you example. Suppose this is a sine wave, okay. So sine wave can be represented between two lines, one line and this line. So this is a bounded curve because the maximum value and the minimum value will be in between 1 and minus 1. Therefore all the values of y equal to sin x will be in between 1 and minus 1. Therefore it is a bounded set, okay. But if I am drawing a parabola, okay, if I am drawing a parabola, it will be like this. So y equal to y square equal to 4x. This is unbounded because there is no upper limit of this curve. So this is the difference between bounded and unbounded. So the theorem for unboundedness is I am going to explain it. Unboundedness theorem. There are two parts of this theorem, okay, one for the primal and other for the dual, okay. The theorem is stating that if the primal problem is feasible while the dual is not, if the primal problem is feasible and the dual is not, the objective function of the primal is unbounded, ठीक है. और बी पार्ट में इसी का जस्ट उल्टा कहा गया है कि ड्यूअल आपका फिजिबल है और जो आपका प्राइमल है वो आपका फिजिबल नहीं है, तो उस केस में ऑब्जेक्टिव फंक्शन ऑफ ड्यूअल इज अनबाउंडेड, ओके. सो आई एम राइटिंग दिस थ्योरम बिकॉज if you want to prove a theorem, first of all you have to understand what is the actual statement of the theorem. If the primal problem is feasible while the dual is not, the objective function of the primal is अनबाउंडेड, ओके. अब बी पार्ट में क्या है, जहां आपका प्राइमल है यहां आपका ड्यूअल है, ठीक है, और जहां आपका ड्यूअल है यहां आपका जो है प्राइमल है, बाकी स्टेटमेंट सेम है, ठीक है. तो क्या बोल रहा है कि प्राइमल प्रॉब्लम अगर जो है फिजिबल सॉल्यूशन देने वाला है जबकि ड्यूअल जो है नहीं दे पा रहा है, तो प्राइमल का जो ऑब्जेक्टिव फंक्शन है वो अनबाउंडेड होगा. यानी कि प्राइमल का ऑब्जेक्टिव फंक्शन अनबाउंडेड होगा तो उसी केस में प्राइमल फिजिबल सॉल्यूशन दे पाएगा जबकि ड्यूअल आपका फिजिबल सॉल्यूशन नहीं दे पाएगा. सिंपल सी बात ये कहा जा रहा है यहाँ पर. नाउ लेट अस प्रूव इट. So first of all, in this case also, let us suppose that x0 is the feasible solution of the primal problem, because the start of the theorem is from the feasible solution. Therefore, first of all, let us suppose that x0 is the feasible solution. x0 is the feasible solution. ठीक है, feasible solution किसका? of primal problem, of primal problem. ठीक है, तो प्राइमल का सोल्यूशन है, तो वी कैन राइट द इक्वेशन एज एफ एक्स इक्वल टू सी टी एक्स. ओके, इसको x0 नहीं, इसको जो है सिर्फ x करते हैं हम लोग, है ना, ताकि आसान रहे. आसान रहे, हाँ. तो x यहाँ जो है फिजिबल सोल्यूशन है, तो देयरफॉर वी कैन राइट द प्राइमल इक्वेशन एज दिस वन. ओके, सच दैट it will be having its own condition such that ax should be less than equal to b and x should be positive number. X should be a positive number. Now I am going to write the inequality of the dual problem. So what is the dual problem? The inequality from the dual, we can write it as a ty is greater than equal to c. ठीक है, ये जैसे जो है प्राइमल का इनइक्वलिटी है, इसी तरीके से ड्यूअल का भी इनइक्वलिटी था ना, जो मैंने लिखा था, तो है ना, याद है क्या था? जी वाई इक्वल टू बी टी वाई such that a t y greater than equal to c and y greater than, ना, ये इसका ड्यूअल था. तो फ्रॉम द इनइक्वालिटी ऑफ ड्यूअल वी कैन राइट a t y is larger than equal to c and y was greater than equal to 0 because there are two inequalities in this case. So for this case there exists a solution. There exists a solution of a z is less than equal to 0, c t z is greater than equal to 0 and z is a positive number. So if this is an equality of the dual, then we can say that dual of dual. Okay, dual of dual, we consider this is the actual problem in this case. And now if we write the dual of this dual, then it will become like this. Okay, because the transpose of transpose will become as a, and in place of y we have taken another variable because we are taking the dual of this dual. So I am taking another variable as z, and it is the larger sign, therefore its sign will be changed because it is the dual of this dual. So I am writing this thing as here. So and the condition will be changed also, so that the new variable is a positive number, therefore I am writing the new number like this. And if this number is larger, then we can write it as and then x0 plus mu z is a feasible solution. A feasible solution. Why? Because x0 is a visible from here. Okay, because here x, not x0, I have changed it into only x. So x plus mu z is a feasible solution. Why? Because ax is less than b. So to make equal to b, we have to add some of the variable here. So I have included a variable like this, a slack variable z and mu. Okay, so in this way it will be a feasible solution. for the primal problem. For the primal problem, for all mu is positive and function of x0 plus mu z, if you put this value into the actual function x0, because it is proved that it is also a feasible solution of the actual problem, therefore we can write this problem into the actual equation, and the actual equation now becomes f x0 plus mu z equal to ct, this is x, not x0, ct x plus mu z. We can write it because it is the actual solution from the actual solution, from the actual solution. Okay. So in this way, this is proved that if the basic problem is feasible while the dual is not, the objective function is unbounded, because this function is an unbounded function, therefore it is proved here. Now we are going to take an example what is the dual. So for this I have given you some of the video